designing and documentation of LEED, GRIHA, and IGBC certified residential and commercial projects in India. We also have Lisa Ferretto, who is a principal architect and sustainability director at Horde Copland Mocht, where she consults on many projects across all studios, promoting the integration of sustainability and well-being throughout the design process. Lisa describes herself as an urban scientist studying the interconnected systems of people with each other, nature, and cities. She is a member of the Baltimore Sustainability Commission and a former member of the Maryland Green Building Council, advocating for environmental equity. During the second session, we have Daniel Overby, who is an assistant professor of architecture at Ball State University and the director of sustainability for Browning Day in Indianapolis. His work focuses on high-performance building design and construction, environmental systems research, green building certification services, energy life cycle assessment modeling, and resilient design. Ahmed Masili, who is currently in the last semester of his Master's of Science in Sustainable Design degree at Jefferson University, and is a Global Goals Ambassador to the United Nations for Sustainable Development Goal 11, making cities inclusive, safe, resilient, and sustainable. He is also an adjunct professor at Minia University in Egypt and was selected as one of the top 50 Egyptian scholars by the USA in 2019. He has won several national and international design competitions. And then we have Al Mitchell, who is a building performance enthusiast and is currently on staff at FIAS. And lastly, we have Mike Radio, who has a wide-ranging involvement in high-performance building design at Ballinger, a local Philadelphia firm. Collaborating with multidisciplinary teams, he has leveraged IESVE and other analysis tools to rapidly generate comprehensive architectural design variation analysis. Starting from the earliest stages of planning. He was recently named 2020 Global User of the Year for the Advanced Energy Modeling Software, IESVE. All right. So with that, we're going to begin our session with a short introduction to systems thinking. While it may seem like the conversation is abstract at points, I promise it will all tie together in the end. So Donella Meadows wrote this primer, Thinking in Systems, as a toolkit for how to develop systems thinking skills. Learning to think in systems is an important first step towards solving the problems facing the world. War, hunger, poverty, global warming, these are all complex problems, and they cannot be resolved by fixing one piece in isolation, because seemingly minor details can have a big impact. And systems are complex, but learning how to think in systems can help us break down the complexity and make steps towards change. So, and we need to change the way we approach design to meet the 2030 challenge and create a more sustainable future. All right, so Donella Meadows starts her primer with an Indian parable about 6 blind men and an elephant. The men had never come across an elephant before and experienced it for the first time by touching different parts of the elephant. The blind man holding the tail thought it was a rope. The blind man holding the legs thought it was a tree. They described the elephant from their limited and subjective experience with each blind man, believing that he has the correct answer. So we have to be very careful not to be the blind men when using energy model or other building performance simulation to inform our design decisions, right? We can't focus on the idea that there is one universal performance metric that will always work and it is the only way to solve a problem. We have to keep a very open mind. And so about keeping an open mind, how many folks have heard a client, boss, manager, or team member say, that's the way we've always done it, or that will never work here? We should stop taking rules of thumb and design precedents at face value and start considering the unique nuances of each case study or example to see how it can be adapted to a completely different project. So how do we implement that? We do that by first recognizing that we don't recognizing what we do not know. If you're using building performance simulation correctly in the design process, you are learning something new with every project, because despite how similar projects may be, in the end, buildings are complex and seemingly minor details can have a big impact. So in this session, we will be looking at massing, orientation, and envelope, but they might not be the primary problem for your study. There is a hidden side to everything, so we should try to understand the complex relationships between decisions made in each phase of the design process. In the book Freakonomics, it explores how we can start thinking in systems about the hidden side to everything. The book is focused on a couple of overarching ideas, many of which can be applied to how we approach design. I'm going to focus on number 3 in the next few slides, because when we get results from an energy model, we need to understand what design features or decisions created the most dramatic effect on the results. Then only can energy models be used or be useful in impact design. We talked a bit about number 2 in the previous slides, where we saw the graphics of wisdom from Adam Grant. And we will also come back to the idea of knowing what to measure and how to measure it later in the presentation. So there's a chapter in the book dedicated to the question of where have all the criminals gone? The authors conducted research to determine the 8 most common explanations for this question. They used the LexisNexis database and combed through articles published by 10 of the largest newspapers spanning a 10-year period from 1991 to 2001. The results are shown in the chart above in order of most frequently used explanations, right? So the authors found that some of these explanations had a plausible contribution to the drop in crime rates. However, the other citations actually don't show strong correlation or causation. There was something far more distant in nature and seemingly disconnected that did show a strong correlation to the drop in crime rates during the 1990s. Is there anyone on the line who wants to unmute and maybe take a guess at this, who hasn't read this? 1, 2, 3, no. So the answer was, it was actually the passing of the abortion rights in 1973. So what does abortion rights have to do with dropping crime rates in the 1990s, nearly 20 years later? Well, the authors argue that once women were able to have children when they chose to have children, those children grew up in a more stable environment and were less likely to engage in criminal activity. When we think about this in the context of buildings and energy modeling, there could be many reasons for why one design strategy has a different, or a couple of design strategies have different or similar EUIs. We need to be able to isolate factors that are not likely to impact energy use or energy loads respective to the current stage of design. This is where single aspect energy models are the most useful. They allow you to dive into the details and ascertain which design decision has the greatest impact on energy results. And those are the kinds of studies that our presenters are going to show today. So coming back to the idea of knowing what to measure and how to measure it, to make a complicated world much less so, you have to be able to define the problem that you're trying to solve. In the follow-up book to Freakonomics, the authors dive into the best way to properly define a problem, or better yet, redefine a problem. So in this book, there's a chapter that dives into the world of competitive eating, specifically the annual Nathan's Hot Dog Eating Competition. In the year 2001, Takeru Kobayashi doubled the previous record. The previous reigning champion had a record of eating 25 hot dogs. And here comes this skinny Asian guy who blows the record out of the water. How does he do it? How does he double the number of hot dogs previously eaten? Well, the answer is kind of simple. He does it by rethinking the purpose of the competition. Yes, the purpose is to eat the most hot dogs, but he approaches it just slightly differently. He says, how do I make hot dogs easier to eat, right? He recognized that when eaten with a bun, the doughy bread dried out his mouth and slowed him down. So instead of washing each bite down with water, he separated the buns and the dogs, soaked them in water to eat it faster and followed up with the hot dogs. So he isolated the specific problem to come up with the best solution. And that's how we want to approach energy modeling in early stage design. So how do we do this for buildings, and what should we consider first? The first question that I always think about is, where in the world are you? And that's a macro level question, right? What climate zone are you working in? And then looking at what kind of building is it, right? That's very important, because different building use types will indicate whether or not it's internal load dominated or skin dominated. And that will allow you to decide what you need to focus on. Do you need to focus on your skin, or do you need to focus more on massing and orientation? And then at a micro scale level, what is the context that you're working in? You know, within a climate zone, you still have different microclimates depending on your surrounding context, right? So we're gonna talk a little bit about the architect-engineer relationship and how it relates back to those questions. The architect's decisions determine heating and cooling peak loads. I think this is really important to emphasize, because heating loads and cooling loads or peak loads are very different than the amount of energy that your building actually uses. There's a great emphasis on EUI, and EUI has its purpose, but it's not necessarily the metric that architects should be focusing on in the beginning of the process, because we have to find ways to reduce our loads so that our systems can be small, cost-effective, and more energy efficient, and ultimately result in the lowest EUI possible for your building, right? So this is thinking like an architect and an engineer. And I'm gonna do a little advertising here, since one of the many hats I wear also includes content management for Ladybug Tools. So this is hot off the presses that was completed this weekend. And if you're a Ladybug Tools user, the next update coming out in a couple of weeks will now include a new Honeybee component that simplifies the architect's ability to visualize peak loads as they relate to design changes. So this is something that's really exciting, that's gonna make it much easier for us architects to engage with these kinds of tools, right? So last two slides here. Summarizing everything that we've talked about, you know, we have to understand the terms and conditions of our energy modeling. So no more rules of thumb like, how far should I put my window? Let's start thinking about it in systems and understand things in order of magnitude, and customize our workflow for each project. You know, what worked once might not work the same again. And, you know, we really have to start thinking about building performance modeling kind of like a cost estimate. Costs will be different depending on the reference you use, the methodology, like if you're doing unit cost versus square foot. What city you're in is going to determine what that ultimate cost comes out to be. And even though cost estimates are never 100% accurate, you still need them to make go, no-go decisions, right? So we really have to think about things differently. And then, of course, we have to put a disclaimer on the studies that we do. These studies are not meant to predict EUI. They're not meant to be 100% accurate. They're meant to help us make those decisions that are important earlier on with respect to reducing our loads so that our systems can be right-sized and ultimately we use less energy. Okay, so with that, we're